Hey everybody, today we're going to talk about one of the 6 mechanisms of how antimicrobial drugs affect pathogens, and we're going to talk about selective toxicity and what that means. So I'm going to start by going into some of the background of the subject matter for today. So to get started, we're going to talk about Paul Ehrlich and how he was a visionary as a German scientist, and he was one of the first people to propose the term chemotherapy. Today we know the term chemotherapy as a broad term for cancer treatment, and that's something I'm sure that he wasn't really thinking about when the term was coined. His definition of chemotherapy was the use of chemicals that would selectively kill pathogens while having little or no ill effect on the patient or host. Later on, he started to write about magic bullets that would bind to receptors on germs and completely ignore the host cells. Now, we know today that is not fully the case. He identified arsenic compounds during his work that worked against certain microbes, one of the more notable ones being against syphilis. During his groundbreaking work, he laid the way for many others, including Alexander Fleming, which was the discoverer of penicillin, Gerhard Domack, and Selman Waksman. And the combination of all these scientists' work ended up coming up with the term antibiotics that we know today. So now I'm going to shift over to selective toxicity. Selective toxicity relates to an antimicrobial drug being more toxic to the pathogen than the pathogen's host. So going after the microbe or bacteria or whatever's infecting a host and only affecting that particular microorganism and not so much the host. One of the reasons that this is possible is because of the differences of structure or metabolism between the pathogen and the host. There are many antimicrobial agents due to the variety of microbes and bacteria and all the different forms and shapes and species and all those kinds of fun things. So we have a lot of those available to us. Drugs like antifungals, antiprotozoans, and anthelmic drugs are harder to come by due to their cells being more like their animal and human hosts. And then we have very limited access to antiviral drugs because they don't have the same level of efficacy or safety. Viruses utilize the cell or use the host enzymes and ribosomes to replicate and metabolize, so it makes them a little bit harder to narrow down and really attack them. So again, it just plays into the safety and efficacy of the drugs. So there are several ways that a microbial agent can attack a pathogen. There are 2 main methods of action here, and they are broken down into other subcategories. The 2 main methods are interference with prokaryotic ribosomes and the interference with the charging or transfer of RNA molecules. Prokaryotic ribosomes differ from eukaryotic ribosomes in structure and size. This does play an important factor, so just stick with me here. Prokaryotic ribosomes are sized 70S and composed of 30 and 50S subunits. So these subunits play a role here in just a little bit. Some of the drugs in this classification do have negative effects, so we do have to be a little bit careful. These negative effects can affect the mitochondria of eukaryotic cells, and some of these mitochondria that are more affected are going to be in the liver and the bone marrow due to high metabolic activity. So going into the subclasses, so these mechanisms are changing the shape of the subunits, blocking tRNA binding sites, blocking enzymatic activity within some of the subunits, preventing formation of the peptide bonds between aminos, and prevention of the prevention of movement of the ribosome along mRNA with antisense nucleic acids, and inhibiting the initiation of translation altogether. One of the things that really interested me during this reading and conversation was that the lincosamides and macrolides This class of drugs utilizes antisense nucleic acids, which are RNA or single strands of DNA designed to be complementary to a specific mRNA molecules within the pathogen. These nucleic acids block ribosomal subunits from attaching to that of the pathogenic mRNA with no ill effects towards humans, which, wrapping this back to the beginning of, are any of these drugs truly selectively toxic. So, one of the drugs that we have today and we use relatively frequently is that of erythromycin, which is used in the treatment of gram-positive bacteria for a handful of different items. So, just overall, throughout this discussion, the goal here is to understand what the selective toxicity is and if there are drugs out there that are selectively toxic and they're safe. So I picked that erythromycin is selectively toxic towards gram-positive bacteria via any of those multifaceted steps or different types of action. More importantly, it's going to be the prevention of movement of the ribosome to transcribe the mRNA using those antisense nucleic acids. Thanks, guys. One little thing to add here at the end of the video, I'm going to go ahead and add a picture description from the text that helps to describe the different size difference between the prokaryotic and eukaryotic ribosome differences in their sizes. So